There is an important irrational number in math that's called e, and it's about 2.72. The first digits of it are actually 2.7, more accurately 1828. Then there's another 1828, but then after that there's a 4, and it goes off randomly. So it's a famous number in math. I'm going to tell you a little bit about it. Here's a function, f of x equals 1 plus 1 over x to the x power. If you were to plug 1 into this function, it would be 1 plus 1 over 1 to the 1 power, which is 2 to the 1, which is 2. But if you put a bigger number in, like 2, 1 plus... So this thing in the parentheses actually gets smaller as x gets bigger, because it goes from 2 down to 1.5 now. But the exponent gets bigger. And it turns out that when you square it, you get something bigger than 2. You get 2.25. If you were to put 10 in, you'd end up with 1.1 to the 10th power, which would be even bigger. It's a little bigger than 2.59. And if you were to put in, even though you can't really put in infinity, but let's put in a million. 1, 2, 3, 4, 5, 6. You get 1.1, 2, 3, 4, 5, 1 to the millionth power. Now, 1 to any power is 1, but something bigger than 1 raised to a giant power can sometimes become really big. This one doesn't become 1 or something really big. Instead, it becomes about 2.72. And this will be, for us, the definition of e. We could write it this way. E is the limit as x goes to infinity of 1 plus 1 over x to the x power. And it's approximately 2.72. E is an important number in math. There's an E button on the calculator. And there's a button that says ln. We've seen in previous lesson that log base 10 is 1, log of 10 is 1, and log of 100 is 2, and log of 1,000 is 3, because that log has a little 10 here implied. Is what power does 10 need to be raised to? Well, there's also something called ln, and ln of e would be 1, and ln of e squared would be 2, and ln of e cubed would equal 3, because ln is the same thing as log base e. So ln of 10, for instance, is the same thing as log base e of 10. Log base e of 10 is saying e to what power equals 10. Well, e is a little less than 3. 3 squared is 9, so it's got to be bigger than 2, and it ends up being about 2.3. You can solve exponential equations if you have a log base 10 button, but you can also do it with your ln button. You take the ln of both sides. You use the rule of logs that you can bring this exponent down. And that ln 5 is kind of like the coefficient of the x. And then you type into your calculator ln 200 over ln 5, and you get 3.3. The ultimate example, though, for use, so for an example like this other one, it doesn't matter if you use ln or log, but if my question is e to the x equals, well, for that one, if I do ln of both sides, it works out really nice, because the x comes down, ln e equals ln of 500. And I don't need to divide both sides by ln e, because ln e is just the same thing as 1 log base e of e. E to what power equals e? E to the first power equals e. So you just get x equals ln 500, which is about 6.21. You could also do that question by sort of rearranging. We're saying that this is the same thing as saying log base e of 500. X equals a log base e of 500, which is the same thing, just by definition, of ln 500, which is 6.21. So that's e and the related thing, ln, natural logarithm. Something you can do with e is, if I want to compare, let's say I have two functions. I want to know which one is the faster growing function. 5 to the 1.3x or 7 to the 1.1x. Well, 5 is smaller than 7, but 1.3 is bigger than x. And 1.3 is bigger than 1.1. I could calculate 5 to the 1.3 and 7 to the 1.1 and compare those, but I want to do it in a different way. I'm going to rewrite 5 as e to the ln 5, because ln 5 is the number between 1 and 2 that I raise e2 to get 5, so e to the ln 5 is the same thing as 5. I can do the same thing with 7, write it as e to the ln 7. Now I can multiply the exponents, so 1.3 ln 5x versus 1.1 ln 7. And, well, I have to use my calculator to see that 1.3 times ln 5 is about 2.09, and 1.1 times ln 7 is about, there's an x there, 2.14. So it turns out that 7 to the 1.1x is bigger than 5 to the 1.3x. E gets used in a certain type of financial application. So here's compound interest question. I put $500 in the bank. I get 5% interest, so it's 1.05, and I get compounded once a year for 3 years. So the amount of money I'll have at the end is 500 times 1.05 to the third power, which is about $579. Now, if I change the n to 2, then what happens is that I get interest twice a year, or every 6 months. So this becomes doubled, it becomes 6. But every 6 months I don't get 5% interest. Every 6 months I get 2.5% interest. So this number got bigger, this number got smaller. But altogether it's going to be more money. A little bit more money. About $580. So about an extra $1 for that. In general, it would be 500 times 1 plus 0.05 over n, where n is the number of compoundings, to the 3n power. And if I make n a really large number, we're going to get a formula for that in a second. In general, the formula for compound interest is principal times 1 plus r over n to the nt power. But if I can't plug infinity in for n. That's called continuous compounding. But I'll show you a specific example. What if I put in $1 and this bank gives me 100% interest, which is a great amount, but they only let me keep in the money for 1 year. So if it's only compounding once a year, it'll be 1 times 1 plus 1 over 1 to the 1, which is $2. I put $1 in, I get 100% interest for 1 year. If I put in two compoundings, it's 1 plus 1/2, that's basically 50% interest every 6 months, so they do it twice, we get 2.25. You might recognize these numbers from before. And if n equals infinity, we end up with the limit as x goes to infinity of 1 plus 1 over x to the x power, which is e. So you would get e dollars if you put $1 in the bank for a year at a bank that gives you 100% interest, but they compound it what's called continuously. So e is what happens, and that's why maybe it's not too surprising that the formula for continuously compounded interest has e in that formula. It's p times e to the rt power. So if I make that situation before with the $500 and the 3 years, 5%, but n equals infinity, continuously compounding, it's a equals 500 times e to the 0.05 times 3. And we do it on the calculator, it ends up being $581, so a little bit better. But there's our formula. And that formula is good, especially if I want to answer a question like, if I put $500 in the bank, how long will it take, continuous compounding, for the money to grow to double if my interest rate is 3%. So for that one, I say 1,000, that's a, equals 500 times e to the 0.03t. Divide both sides by 500. Get 2 equals e to the 0.03t. Take the ln of both sides, get ln of 2 equals 0.03t. Maybe I should say ln of e to the 0.03t. Bring the 0.03t down, and the ln e becomes 1. Either way, we get ln 2 equals 0.03t. Divide both sides by 0.03. This is the answer, the exact answer. But if you plug that into a calculator, you get 5.3. Actually, you don't. You get 23. An interesting question is, what's bigger, e to the 0.2 or 1.2? Seems like a question that you really can't answer, but I know which one's bigger, and I'll tell you why. 1.2 is the amount of money you'd have if you put $1 in a bank with 20% interest for 1 year, and it doesn't have any, just one time, no compounding. E to the 0.2 is the amount of money you'd have if you put $1 in a bank with 20% interest compounded continuously. So it's got to be bigger than 1.2, and it turns out that it's 1.22, so it is slightly bigger. There was a way to sort of figure that out. Not to figure out this number, but to see that, compare it to 1.2. In a previous unit, we saw that we can take an exponential, like a model for an exponential equation, and we can get it in the form y equals a times b to the x, where b is some growth rate. Well, it's also possible to get exponential equations in the form of y equals y0, which is kind of like a, but instead of, sorry, this should have plus c. Instead of having b to the x, it's e to the kx. E is not a variable, it's the constant e. The k, the coefficient of the x, is sort of related to the growth rate. And I'll show you how to get an equation. The easiest situation is where we know the y-intercept, and we know another point. and we have c equals 0, which is given here. So if you plug 0, 10 in, you get 10 equals y0 times e to the k times 0 plus c is 0 also. E to the 0 is 1, so we get y0 is 10, that's what this number is. Then we take the other points and say 17 equals 10 times e to the k times 5. Divide both sides by 10. Take the ln of both sides. Get ln of 17 over 10 equals 5k. And then divide both sides by 5. And we end up with k is 0.106. So this equation becomes 10 times e to the 0.106x. And the 0.106 kind of tells us about the growth rate. It says that it kind of grows at like around 11%. It's more than 11% growth per year, because this is like 11% compounded continuously, but it gives us a pretty good like measure, this approximation of the growth rate. And in a lot of scientific applications, they write their equations in this form with the e to the kx instead of the b to the x that I used in a previous lesson. Okay, the final question is, what if one of the 2 points... Oh, let me say another quick thing. If you have something in the b to the a times b to the x form, it's actually pretty easy to change it into the e form. All you do is change the 1.037 to e to the ln 1.037. That's just a fancy way of writing 1.037. So it becomes 10 to the e times ln 1.037 times x. And this thing on the calculator is 0.036. So it's 10 to the e, 10 times e to the 0.036x. So you can sort of convert from a times b to the x into y0 times e to the kx. And you can go in the other direction by just raising e to the 0.36 power. It will get you the 1.037. Okay, the final question for this is, what if neither of the points, what if instead of 0, 10 and 517, it's 1, 10 and 517? And they have to tell you the asymptote. I'll tell you that it's at 0. So what we do, we have we have 10 is equal to y0 times e to the k times 1 plus 0. I'll put a plus 0 there. And I like to put the one with the higher x value on top, so 17 is equal to y0 e to the k times 5 plus 0. Now if this wasn't a plus 0, I'd have to subtract from both sides, but since it is a plus 0, I can ignore it. Then you divide the two equations, and the y0's cancel out. You get e to the 5k minus k is 4k. We get ln of 17 over 10 equals 4k. And then you divide by 4. As a number on a calculator, it's about 1327. So that's the k value. Remember, there's two things. There's the y0 and the k. To solve for y0, I would take this equation right here and say that y0 is 10 over e to the k. The k we just figured out. And then if you do 10 divided by e to that thing, you end up with about 8.75. So the equation for this curve here is apparently 8.75 times e to the 0.1327x. Okay, so what we've done in this 20-minute video is go over what e is, what ln is, and how e comes up in continuously compounded interest, and how to use e for solving equations. It's a lot for 20 minutes. Hope you liked that video.